Hello. While calculating the efficiency of a reversible heat engine, example a Carnot engine, we substitute Q1 by Q2 is equal to T1 divided by T2. It's for a reversible engine alone. Why? We will discuss in this video. Assume there are two reversible heat engines RHE1 and RHE2 operating between the same two temperature limits. The schematic is shown here. Initially, assume efficiency of reversible heat engine 1 is greater than efficiency of reversible heat engine 2. We know efficiency of a heat engine is work output by the energy supply. Work output is W or HE1 for engine 1 and Q1 or HE1 is the heat supplied for engine 1 and hence efficiency of engine 1 is expressed like this. Similarly, efficiency of engine 2. As per our assumption, efficiency of 1 is greater than efficiency of engine 2. Again, assume if the heat added or supplied to both the engines are equal, let the quantity be equal to Q1. Substitute this value in efficiency equation, we get like this. Since Q1 is same for both the cases, we can write work delivered by a reversible engine 1 is greater than work delivered by the reversible engine 2. Now, let the engine 2 be reversed. When reversed, the heat engine works as a heat pump or a refrigerator. The schematic is shown here. We are reversing engine 2. When we say reverse, the quantity of heat transfer and the work are same, but their direction is changed. Now, to explain, redraw the schematic again. When engine 2 is reversed, it works as a heat pump. Therefore, it requires work input. But engine 1 is still delivering work. What can we do now is supply the work delivered by the heat engine 1 to run the reversed heat engine 2. Now, the net work output is equal to difference in the work delivered by a reversible heat engine 1 and the work consumed by a reversed heat engine 2. How this is valid? WRHE1 minus WRHE2 reversed. Earlier we discussed work produced by engine 1 is greater than work produced by engine 2 as per our assumption. Therefore, this is valid. Now look at the heat supplied to a reversible engine 1. It is equal to Q1. Similarly, look at the heat rejected by the reversed heat engine. Again, it is equal to Q1. What can we do now is, since the quantities are equal, remove the source and directly input the heat delivered by the reversed heat engine to the reversible heat engine 1. Now, remove this first schematic. Consider the one appearing on the screen. This can be enclosed into a control volume, or we can focus our attention over there, wherein we have two devices. One is a reversible heat engine, another one is a reversed heat engine. Both combined together is capable of delivering work by exchanging heat with only one single reservoir. This violates second law of thermodynamics. That is Kelvin Planck's statement. Hence, the assumption efficiency of reversible engine 1 is greater than reversible engine 2 is wrong. Alternatively, if you reverse RHE1, assuming the efficiency of engine 2 is greater than the efficiency of engine 1, again we get the assumption is wrong. And hence, we conclude efficiency of reversible engine 1 is equal to efficiency of reversible engine 2. This is a corollary of Carnot theorem. What it says, efficiency of all the reversible engines operating between the same two temperature limits will have same efficiency. So what is absolute thermodynamic temperature scale? We will discuss. The efficiency of a reversible heat engine is a function of temperature only. This can be written as efficiency 1 minus Q2 by Q1. So Q2 is the heat rejected, Q1 is the heat supplied, is equal to a function of T1 and T2. T1 and T2 are the source and sink temperatures. This can be written as Q1 by Q2 is equal to function of T1, T2. Now it's some other function capital F. What is this function? We are trying to find out that function. For that, consider two reversible heat engines A and B are connected in series. Engine A receives heat Q1 from the source at T1 and rejects heat Q2 at temperature T2 to the engine B, which in turn rejects heat Q3 to the sink at temperature T3. Both engine A and B delivers work. Also, assume there is one more reversible heat engine C works between the temperature limits T1 and T3. Look at this heat rejected by engine C. The quantity of heat rejected by engine C is equal to the quantity of heat rejected by engine B. Similarly, the quantity of heat taken by engine C is equal to the quantity of heat taken by engine A. Engine C is also delivering work. This Q1 by Q2 is a function of temperature, can be written for these three reversible engines separately like this. For engine A, Q1 by Q2 is a function of T1, T2. For engine B, Q2 by Q3 is a function of T2 and T3. For engine C, Q1 by Q3 is a function of T1, T3. This Q1 by Q3 in C returns. So Q1 by Q3 is equal to Q1 by Q2 multiplied by Q2 by Q3. What is this Q1 by Q2? For engine A, Q1 by Q2 is a function of T1 and T2. And Q3 is engine B, it is a function of B. That's what it's only. And Q1 by Q3 is equal to Q1 by Q2 product multiplied by Q2 by Q3 is possible only if these two functions takes the form phi of T1 divided by phi of T2 multiplied by phi of T2 divided by phi of T3. So phi is some other new function. This T2 cancels and we will get Q1 by Q is equal to phi of T1 divided by phi of T3. Or in general, we can write QH divided by QL is equal to phi of TH divided by phi of TL. So QH is the heat supplied, QL is the heat rejected. H stands for the reservoir at higher temperature, L stands for the reservoir at lower temperature, and TH and TL are the temperatures of the corresponding reservoirs. What is this function phi? Kelvin proposed a very simple function. Phi of t is equal to T, and he defined an absolute thermodynamic temperature scale. So phi of t is equal to T. It is proposed by Kelvin, and for a reversible heat engine, therefore, we can write QH by QL is equal to TH by TL. So TH by TL, or we can write TH is equal to TL multiplied by QH by QL. So this is a temperature scale, absolute thermodynamic temperature scale, independent of working states. proposed by Kelvin. Because of this, we can write the efficiency for a reversible engine 1 minus Q2 by Q1 is equal to 1 minus T2 divided by T1. So this is applicable for a reversible heat engine. Thank you.